Mohan. Hello, sir. Professor Akhilesh
Yeah.
Mohan has received BTech degree in Electronics Engineering from Kamla Nehru Institute of Technology, Sultanpur in 2002. MTech degree and PhD degree in Microwave Engineering from IIT Kanpur in 2004 and 2009 respectively. From 2009 to 2010, he was a scientist with the Space Application Center, Indian Space Research Organization, Ahmedabad. From 2010 to 13, he was a faculty member with the Department of Electrical Engineering in IIT Jodhpur, Rajasthan. From 2013 to 20, he was a faculty member with the Department of Electronics and Electrical Communication Engineering in IIT Kharagpur. And since 2021, he has been a faculty member with the Department of Electronics and Communication Engineering, IIT Roorkee. He has authored and co-authored more than 150 peer-reviewed international journals and conference papers. His research interests include the design of microwave filters, antennas, and absorbers for wireless communication systems. We welcome you, sir, for this ATAL FDP talk. Hello.
Thank you, Swarnima.
Welcome, sir.
Thank you for the kind introduction. So I will share my screen and I will be talking about in the next 1 hour on the topic. First, let me share my screen.
Yes, sir. Please check it.
Okay, is my screen visible?
Yes, sir. Your screen is visible, sir.
Okay.
Thank you.
Okay, so good evening, everybody. So I am Professor Akhilesh Mohan from Department of Electronics and Communication Engineering, IIT Roorkee. In next 1 hour, I will be discussing about the beam steering antennas and the reconfigurable intelligence services. What are the basic difference between these two technologies? One is used for 5G communication, and another is used for 6G will be used for 6G communication. I will be discussing in next couple of hours, in 1 hour. Okay. Okay, so here is the outline of my presentation. First, I will give you a brief introduction about the wireless communication in 5G and 6G network, how it occurs. Then RIS, what is RIS? Much has been taught. Just to give some brief overview of RIS, what is RIS and how it is advantageous for the 6G communication system. And then beam steering antennas, and finally I will draw my conclusion for my talk. Okay. So in 5G communication network, if you see, so we have two types of frequencies which are being used for 5G communication. One is sub-6 gigahertz and or microwave we call it, and another is millimeter wave. So and each of them has certain application. Means, let's say if I want to transfer high data rate, I will be use millimeter wave. If I want to transfer the data for larger distance, I will be using the sub-6 gigahertz. So these two frequencies are being used for the 5G communication system or communication network. Okay, so FCC has allocated, 3GPP has allocated some frequency bands for this 5G network. So that is FR1 and FR2, that is frequency range 1, and frequency range 2, that is 410 megahertz to 7125 megahertz. And for this FR2, that is millimeter wave, that's 24 to 52 gigahertz. So we have to communicate in these two bands only for the 5G network. Okay, now here are based on this, the 3GPP has allocated or designed several bands, that is N1, N2, N3, N5 till N95, and at higher frequencies also N257 and this one. Each of them are having some uplink frequency and downlink frequency. And the main thing is that, so each NR band, NR is new radio band, has certain frequencies. So that is bandwidth. Bandwidth is mostly 50 megahertz or maximum 400 megahertz, not more than that. So if you design an antenna system or any system which works as which have the bandwidth of 400 megahertz, that is good enough for one NR application. Okay, it is not likely that or maybe if you design a wideband antenna, so it can be cover more NR frequency. bands. Okay. Now in 5G technology, the basic enabler means what is going to enable this 5G technology is massive MIMO and the beamforming. I will discuss what is massive MIMO. Massive MIMO is just a MIMO, but it is a if the number of elements are greater than 8, we call it massive MIMO. So here, if you see here, they have taken near about 8 cross 8, 64 elements. 64 elements. That is called massive MIMO. And beamforming. Beamforming means this one antenna, one massive MIMO antenna can be used to transfer the beam in all the directions. Means it can be used to switch the beam in all the directions by giving different excitation coefficients that we will discuss how it can be done. So basically, take away from the 5G enabler, that is, it can increase the data rate, or it can. So that is massive MIMO and beamforming. Now, so in 6G, if you move in 6G is going to come into 2030. So it will be basically deployed. It will be basically deployed the lower microwave frequencies and higher microwave, that is in terahertz, that is at 140, or maybe that is at higher frequencies. It will be deployed. Now here the bandwidth available is ultra high. Here it is ultra high frequency band, millimeter wave terahertz, and it supports the high data rate communication, very high data rate in the real time. So why do we need very high real data rate, ultra wideband real time? Because let's say if a robot or maybe a person is doing surgery from the robot remotely, so it has to be real time. Real time means it has to be, there must be lesser latency such that whatever he is doing at the remote at the city, that has to be done in the means at the remote location. So that is why latency has to be less. And so this is so latency has to be less. That can be attained by the, if you use higher frequency bands, and the frequencies also, the technologies which are going to be used is ultra massive. We are talking about the massive MIMO for the 5G. We are 62, 128 antennas are there, and here ultra massive MIMO. Ultra massive MIMO, it is used, but they are planning to do that, but I don't know whether it, so they are planning to do the RIS structure. RIS structure is much better than the ultra massive MIMO. Let's see how this is going to be deployed. Okay, so these are some of the antennas which are available, which are used in the 1G, 2G, 3G, 4G, and 5G communication technologies. In 1G we have used omnidirectional antenna. In 2G, that is single polarized directional antenna, then bipolar antenna, then MIMO, then massive MIMO, and so on. So if we compare the data rate of 5G and 6G, the peak data rate is only 1 terabit, 0.01 terabit per second, or 10 gigabits per second. Here in 6G, it is 1 terabit. It is 100 times. And delay is also 1/10, and reliability is 99.999. Okay, now when 5G, 6G will be deployed, at present in 5G, we have near about 100 devices in the city. I'm talking about the city. So they thought that they have 100 devices in 100 square meters, and now the devices will be also increased manifold, that it will become 1,000 devices. Then how to control the bandwidth? So then they have to search some new avenues to handle this large number of devices. Okay. Now the key feature for 1G to 6G communication in 5G, the massive MIMO, and 6G is the RIS structure. I will talk about these two here in this lecture, in this class. Now in 6G technology, so the new paradigm, new interface, new spectrum, new architecture, new networking, everything has to be thought of. How we are going to enable that. 5G, we are saying that we will be using massive MIMO, we will be using beamforming network, all these things, so that we need to solve. It is still in the upcoming evolution phase. Now, in the new spectrum, regarding the new spectrum, that is spectrum wise to millimeter wave, that is 30 to 300 megahertz, then terahertz, we use tera at 1.1 to 10 terahertz, and new interface, that is massive MIMO and RIS. So RIS will be that they will be using metamaterial structure, and new networking, all other new, that is AI, blockchain, all this thing has to be intelligent communication, secure communication has to be enforced for the 6G communication technology. Here are some of the applications of the 6G technology, that is metaverse or virtual reality, then automatic driving, that is intelligent transport system, then intelligent manufacturing, means the robot will be manufacturing precisely, and holographic intelligent medical service, that what I was talking about, this doctor is doing the real-time operation performed by the robot, and then network UAV and smart city. These are some of the applications. Now introduction to RIS, that is reconfigurable intelligent surface. Now the physics of wireless signal propagation. Now electromagnetic waves travel at the speed of light. It spreads in all the directions. So according to Farrell's transmission formula, so if the received power at a distance d will be your transmitted power over the area, that is aperture area, and all, that is 4 pi by d square. So if we take, let's say, if we consider the frequency of 3 gigahertz, so at 1 meter distance, you will get minus 43 dB power down. If it is 0 dBm is there at the transmitter, so you will get minus 43 dBm. And at 10 meter, you will be getting minus 63 dBm. That is very less power. Hardly, only tiny fraction of power is received at the transmitter end. Now, this is if you have the line of sight communication, means there is no obstructions in between that. Now, if obstructions come in between that, that is example of the walls, curtains are present. So the wall will have again minus 20 dB down, then extra path, multi-path fading, and all this thing will further degrade your signal, degrade the signal. So you, as we were talking about the minus 63 dB, so it will become minus 83 or 85, 86 dB down. So it is because of the reflection, scattering, and diffraction from the edges. Now, okay. Now what is the RIS? So RIS helps in shaping the scattered signal. So what happens if we apply some RIS in our room? So what is going to happen? So whatever the signal we are getting from the transmitting antenna, that is base station, so will impinge on this RIS, and it will focus. It will try to modify the beam direction. It is something like curtain to maybe passive, or maybe that is passive or active. That I will discuss. Okay, passive or active. So it can be moved in any one of the direction. So that is depending on the how we design the RIS. Now RIS, that is reconfigurable intelligent surface. Reconfigurable means whose properties can be changed. So properties. So generally in reconfigurable antenna, what we talk about? We say reconfigurable antenna means if we reconfigure the frequency, we reconfigure the pattern, we reconfigure the polarization. But here in the RIS, what we reconfigure the pattern of it. The pattern, yeah, we don't reconfigure the frequency, we reconfigure the pattern of the incoming signal. Okay, intelligent means it has to be real-time programmable and controllable. Means what, let's say it is coming from some another direction, this direction on this surface, so it has to modify accordingly such that whatever the receiver which are present in the room, so will get the good amount of signal, receive good amount of signal. And surface, it is two-dimensional array of scatterers, 2 dimensions, so it is called a surface. So that is RIS, reconfigurable intelligent surface. Now, how it is designed? It is just a element patch. A patch is there on the back. It is connected to a diode. So diode will connect it, means it will be connected to the ground, or it will be controlled by some controller, that is by FPGA. So here you can observe numerous number of patches are there. So we can switch on and on the patches and switch the beams. So here, if this is the transmitter, if I want to transmit this to user 1, user 2, or user 1, so I will use one distinct pattern. If I use to transfer to another user in another direction, I will use another pattern. Single element makes only little difference, but if you have a large number of elements, so you will be able to make switch the beam entirely. Okay. Now the question comes, how large are these elements? Whatever these elements are very large or very small. How large? Generally, it should be the surface, the RIS should be that is continuous. But in practical, it is not possible. That is, continuous surface is not possible. So it has to be discretized. Yeah, it has to be discretized. Now what researchers has proved that if you choose lambda by 2, then you will not have the gain in all the direction equal gain. Means it will scatter of something, some in another direction. Means some signal will be enhanced, some signal will be degraded. Now, if we choose lambda by 8 cross lambda by 8, that is sub-wavelength, then what is going to happen? So you will have 0 dB, means at all the incidence angle, it will affect the same. So it will. So generally, this is the theory of sub-wavelength metamaterial. So it should be metamaterial. Now, so here this RIS, it is reconfigurable. So how it is applicable? So it is means it controls the directivity of the scattered signal, it controls the signal absorption, and it controls the polarization. it improves the indoor coverage in a mall or in a building, in an institute. So it will improve the in coverage, and it will protect against the eavesdrops. Means your signal will not get leaked to another, and it will mitigate the shadow fading. Shadow fading means if you are in the shadow region of your base station, so you will not get signal properly. So it will scatter the signal and try to send you the signal to such that you receive the good amount of signal. Now, the work on the RIS started back near about 12 years back. So with different names, they called it intelligent walls. They called it software controlled metasurface, then RIS, and that is AI metasurface, intelligent surface. But now they have all come up together and they have coined this RIS. So they will be using a reconfigurable metasurface, this term. Okay. Now, background also of RIS. So it is an array that is composed of a large number of reconfigurable sub-wavelength, and each element can be adjusted. It can adjust the electromagnetic properties of the incident wave, so to intelligently reconfigure the wireless environment. Now, so here each element means each element of the RIS. So we have, let's say, n cross n elements. So each element has to be especially reconfigurable intelligently so that you can transfer your beam in a particular direction. Now, this is the classical communication. So classical communication, whatever we are having at present. So here is a transmitter, another is a receiver. So if transmitter transmits some amount of power here, so the receiver will get very less amount of signal. Very less signal will be received by the receiver. Now if this RIS aided communication, this means the communication which has RIS. So if transmitter is there, so now this RIS, what will the function of RIS? RIS will try to focus whatever signal it is receiving here, focus the beam into the another RIS such that the signal which are received by the receiver is good enough. Means you do not require anything. So now RIS has to be placed on certain walls where the buildings and all this buildings and the towers, or maybe that is they are blocking the signals. So there RIS has to be deployed. Now RIS, that is history of RIS. So it is basically RIS uses the metamaterials. So metamaterials are artificial materials with a structure that exhibits unnatural properties. Unnatural properties means they are the properties which are beyond the extent of nature. That is why it is called meta material. So it is basically which cannot be occurred in a natural occurring materials. Now the 2D equivalent of the metamaterials are the metasurfaces. So that is, metamaterials are the point for the 3D structures. So that is 2D structure are the metasurfaces, which are the basic unit element of this RIS. So there are different types of metasurfaces are there: electrical, magnetic, thermal, light. So we'll be discussing only the electrical in this lecture. So this is some optical metamaterial, then this is electrical, this is also electrical metamaterials. So they will they will switch, or they will try to bend alter the properties of the wave, incoming wave. Now, so RIS, the fundamental, can be viewed as a reflective array composed of a large number of sub-wavelength programmable elements. So here, if you see, you can observe. So it is something like 8 cross 8. So the patches are there. At the back of the patches, you have a phase shifting element. It can be pin diode, it can be vector diode, depending upon the, if you want to switch on or off, or if you want to alter the beam, I mean, do that. So all these things will be controlled by, so on off has to be controlled by the this one, controlled by the FPGA programming. That means whether you want to means what number of means what should be the on, how many patches are on, how many patches are on off, such that it can shift your beam in a particular direction. Okay, so this is RIS. So prototypes has been demonstrated not long back. They have demonstrated in 2020. That is in MIT. The recoverable wall they have demonstrated. The painting types of structure they have demonstrated in China, Japan, and China. And they have demonstrated transmittive type of RIS structures. So basically, Japan, China is working a lot on this RIS structure. Now, so what are the advantages of this RIS aided communication? So it will overcome the blockage and provide additional communication link, enhance the signal quality, increase the spectrum, and save the power consumption and increase the energy efficiency. So you can see here. So now the tower is there. So if we, let's say, yeah, okay, now if you if you use RIS, this one here, so this car will be getting good amount of signal in place of direct, because maybe in direct communication link it will be getting some cars will be going nearby and so on. Okay, now what are the limits of RIS? So if you have numerous that is natural occurring material, because you cannot apply on the trees, you cannot apply on the RIS on the trees, that is multiplicating effect, then we have to think of another way. So another way thinking is use of active RIS. Active RIS means just this passive RIS doesn't have any means without any it doesn't amplify any signal, but the active RIS amplify the signal with the usage of power amplifier. If you see here, that is, it will just amplify. You are not getting signal here, so it will be just sending here, and this will be transmitting. The transmitter will be transmitting, and it will be reflecting here. So the signal which is getting, which the receiver gets here, is weak in nature. Now, if you use this active RIS, where the phase shifter, whatever phase shifter we have already have here, phase shifter and the reflection type power amplifier is there. So you will get the signal, good amount of signal at the receiver end. Okay, so now based on that, so we have people have designed active type, reflection type of power amplifiers. I'm not going to the detail of this one. So people have started working, and once the concept of RIS came, then people have started working on the reflection type of power amplifier for the its application in the RIS. Okay, now so this is some of the, so this is the basic concept of RIS. Now this is one of the work just we have started 1 year back by one of my PhD student, not PhD and MTech student. That is 2-bit tunable unit cell quad band reconfigurable RIS. So this is the unit cell whatever we have proposed. So here it is something like we have the square patch, and that is U-shaped cell, and they are connected here, and a ring type of structure is there, and 2 diodes are there, and it is short circuited at this one end and another end. And we have applied the two vector diodes whose capacitance can be changed from this 0.45 picofarad to 7.2 picofarad by changing the bias voltage of, that is 1 to 28 volts. Now, so for understanding the unit properties of unit cell, first you need to simulate the unit cell and understand what are the characteristics of this unit cell. So what we found that, so So here what we have, so this unit cell have 4 frequencies. It is a quad band. It is quad band RIS. So 4 frequencies, 4 resulting frequencies. So that is frequencies which lies is between 2 to 10 gigahertz. I will discuss, and each resulting frequencies will have the phase shift of, that is 4 phase shift: 0 degree, 90 degree, 180 degree, 270 degree. So each will have 1 phase shift. Here this first frequency, second frequency, third, fourth. Now for each corresponding frequency, if you want to get this phase shift, so you have to use the corresponding bias voltage to get the to get the capacitor, to get the phase shift. Now this has been proved by this one. So here, if you observe here, so for the first frequency, it is 3.5 gigahertz. So the first one, that is black one, we will be getting around the phase is shown. Phase, okay, this side, the phase is shown is 0 degree, and then as you move from here, that is the phase 0, that is 0, 90 degree, 270, and 180 degree. In a similar way, all of them are having the same thing. Now, okay. So this is the unit cell. Means if all the diodes, means all the vector diodes will be biased properly. So maybe this part of the structure is responsible for the first resonant frequency. This part is second resonant frequency. The center one is third, and entire one is for the fourth resonant frequency by plotting the surface current distribution on the unit cell. Okay, now to use this, excite this means to see the observation whether we want to get the RIS characteristics. We want to switch the beam or not. Can we switch the beam or not? So we have used a wideband antenna, that is antipodal antenna, antipodal Vivaldi antenna, which is hair comb shaped structure. So it covers all the frequencies from 2 to 10 gigahertz. And so now here, so 20 cross 20 unit cells are whatever we have discussed. Unit cell is there, and it has placed at around 138 distance. Now each frequency, generally it has to be, if you have one frequency, not no problem. But if you have a 3 to 3 more frequencies, then what is going to happen? Generally, it has to place, antenna has to place at the phase center. Phase center means at its phase center. So you will have this one. So feed antenna has to be placed at the phase center, the focus of this. So now there are different types of, that is illumination and spill over losses. So now what we want to show you here. So if here it is showing that is the white one is having the phase shift of 0 degree, then we have this one, this is somewhat lighter, 90 degree, 180, 270. Now, so this is the structure. If I want to, this is 0 degree, that is theta. If my beam is at 0 degree, that is we have shown here red one. Now, if I want to switch my beam to 40 degree minus, that is, so what I will do here, I will switch all the elements to this one by using the different bias voltage of the vector diode. Means this pattern has changed to this one. Now in here your beam can be switched. Now that is, beam is on now for the second frequencies. It is the same thing. Beam can be switched as 30 degree. It is more visible at, means you can see, observe that is beam you can switch your beam in the that is at higher frequencies here, and that is at much more higher frequencies, that is at 8 gigahertz. So you can switch your beam from 30 degree to 80 degree, and 0 to 80 degree here in this. And here you have the scan loss is there. Scan loss of near about 4, 5 dB is there. Scan loss means, so at 0 degree, whatever you are having this one, and what is the another amount of losses we will, means what is the amount of loss, gain, how much degradation in the gain, that is called spill, not spill, what is the scan loss. Now based on that, so we can, that is 20 plus minus 28 plus minus 23, 70 degree and 76. Okay, so this is just to give you what is RIS. Now, introduction to beam steering antennas. So what is beam steering antennas? So first of all, so beam steering antenna is just an antenna. So it can change the direction of the main beam radiation. How it can change? So it can alter the phases of the different RF signals to drive the elements or by switching the elements. So the beam steering advantages, it can improve the gain and directivity, reduces because beam is focusing in one particular direction, it will reduce the interference, conserve the power, and focuses on the narrow beam. So now I will discuss 4-5 methods how you can switch your beam, how you can beam steer, how can you steer your beam. Okay. Now first one is most popular thing is used is that is Butler matrix approach. So here I have just shown you the 4x4 Butler matrix. In Butler matrix, let's say here, so it is 4x4. 4x4 means 4 input ports, 4 output ports. So it has some network structure. It has branch line coupler or hybrid coupler, then phase shifter, then again branch line coupler, and this one antenna will be connected here. So till here the Butler matrix. So now if I use this, if I feed P1 only, so what happens? You do all sorts of calculation. What type of calculation? You see how much phase shift we are occurring from the branch line coupler, that is hybrid coupler, then how much coupling you require, how much phase shifting you are getting from the phase shifter, then again branch line coupler. Basically, if I feed P1, see what is the amount of phase difference you are getting at all the ports. Means you will get different phase differences. If you feed P2, corresponding different phases will be there. Similarly, P3, P4. So now for each excitation, you will have one beam. That is maybe this P1, P2, P3. It is not symmetrical. Maybe just you will have different beams are there. So now here, what is you have to intelligently choose the values of phase shifting. How much phase shifting do we need for the Butler matrix? This is layout of the Butler matrix. So what they have shown using the metamaterial. So they have used a branch line coupler. That is branch line coupler. Then crossover is there. Then again hybrid coupler. Then phase shifter. And this they have shown. And they have connected here. So these are the input ports. And these are the 8 output ports. So if I feed P1, so you will get different frequencies, phase shifts and different frequencies. So it is something like if the different antenna elements are excited with the different phase shifts, then you can find out the array factor and get the radiation pattern. Okay. So this they have fabricated it. So they have used it for the 5 gigahertz, something like that. So here it can be shown. It is shown there. So that is if P1 is there, so they have that is minus 15 degree. If P2 is there, minus 40 degree beam steering. Then if P3 is there, minus plus 40 degree, and if P4 is there, so plus 15 degree. So what I want to say here, so here just you have to feed the power for one port 1, port 2, port 3. You can switch your beam to the particular direction, in what directions you want. Okay. Now this is one of the SIW they have shown. So just the technique remains same. Only the modularity remains same. Only the realization of the component, how you will realize the hybrid coupler, how you realize the crossover circuit, how you realize the phase shifter, it will remain same. The same concept is there. So here, and how much phase shift you want. Correspondingly, basic thing is that you have to do the analysis beforehand. How much phase shift, how much beams do you want? So how much phase shift means do the mathematical calculation by hand and get the how much do you want, and we can do, you can find it. So this is, they have done it for the Butler matrix SIW. Now this is 8x8 Butler matrix. So here 8 ports are there, 8 output ports are there, antenna ports. So here, if you observe in the air, it is not simpler, just because it was four beam was there. Now it is some 8 beams are there. So you can switch your beams in much more larger directions by using the 8x8 Butler matrix. Here it is the crossover, then hybrid coupler, crossover, and you have to calculate all this. Means do it mathematically and calculate all the what are the phase shift do you want. That is phase phase shift, whatever you are getting at the antenna. This one, 1, 2, 3, 4, 5, 6. And from that, you can calculate the from this one, that is from array factor. If these are the phase shift for these arrays, then how much amount of tilt in the beam I will be achieving. Okay. Now, beam steering using operational amplifier. This I found very good in the literature, but it has a disadvantage that it can be used only at low frequency, maybe below 3 gigahertz, not more than that. So it just uses a very simple concept. I found one simple paper. So here it is something like that. So it is you have the n number of arrays. So n number of arrays will have the progressive phase shift of 5, that is 5, 2, 5, 3, 5, and so on. So they will constructively interfere and give the direction, give the beam in a particular direction. Now, so how to do that? So what they did it. So they have basic thing is that they have to generate the phase difference of 5, 2, 5, 3, 5, and so on. So the phase difference is generated by this op-amp based circuit, that is phase shifter in op-amp, but only at lower frequencies, not at higher frequencies. That is, so they have used it. So and used. So this is for the that is 5 phase, 2, 5, 3, 5, and 5. So this they have used. Now, if and they have used on the patch antenna, and they have connected these things on the bottom of the phase shifting, the feeding of the op-amp, all these things from this V out 1, V out 2 to this port 1, port 2, port 3. And what they observe here, so they have done this time domain analysis. So if they see the time domain analysis, for first 20 seconds, nothing is visible because it will build up. Then after maybe 30 seconds, so they will observe the continuous phase shift between the signals. So continuous phase shift signals is observed. So that is desired. The phase shift, that is T1, T2, T3, T4, the phase shift is observed. And so it can be observed from, and this phase shift can be changed. It means it can be by, okay, it can be also further changed. You change your phase shift by changing the bias voltage of this one. Whatever this bias voltage, V plus, V minus, no, not V plus, some bias voltage, I don't know what. Some voltage is there. So some bias voltage there, I don't know. Maybe some input bias voltage. Okay, then you can switch your beam in a particular direction, that is 19 degree. Means if you change the bias voltage, you can switch the beam from 90 to 32 degree. And the advantages of this, it can control any large number of radiators. It can generate phase without any limitation in the phase difference, but it can generate all the phases just in the bias voltage. And there is no limited in the phase difference, and all the phases are continuous in nature, no discrete phases. Now, the dual slant cavity bag massive beam antenna with beam forming. So here they have they have used the massive MIMO concept. So here just a dual that is dipole is there, which is dual polarized. Dual polarized, they have two dipoles which are placed at plus 45, minus 45 to each other, and they are fed by the dipole. That is, they are fed by the balloon, because dipole has to be fed by the balloon. At the input side, you have to be fed only one thing. So now, so this is cavity bag. Cavity bag means at the back you have the cavity. So now it can be observed from here that if the cavity, not here, that is if the cavity height is increased, so your beam width is getting narrower, means beam width changes. It is true also if you change the cavity height, or if you change the cavity height, you change the beam width, or yeah, you can change the addition pattern. So one of the advantages of this massive, one of the major challenge of the massive MIMO, you choose the cavity height such that its E plane and H plane beam width are same. Then you will have very excellent performance. Listen properly, E plane and H plane beam width are same. So you have to choose accordingly that cavity height. So based on that, they have designed 16 cross 16, that is 4 cross 4. This one, that is MIMO pattern, MIMO, that is 16 element. So that is 4 cross 4. Now it uses digital beam forming. So now here, if you use 4 cross 4, you will have some beam will be tilting from that is 0 degree, then 10, 20, 30 degree in 5 plane. And if you use higher order, you can switch much more beam. Main thing that it will use digital beam forming, and digital phase shift is applied here. Here we need not to have the complex Butler matrix or the circuitry. Means you have to in the processor, maybe in the processor in the FPGA you have to write code such that it generates a phase shift of this one, and you feed the signal such that it will each the element will have phase shift of this one, so you will get the tilting of your switching of your beam. And so this is your one single beam. This is 4 cross 4, 16 cross 16. Means as you go on the, if you increase the number of elements, so your beam will be much more shift, much more narrower, which will have high gain. So, and also it can be used for certain applications. Maybe let's say if you have multiple users at a single time, so if you want to switch to the multi beams, so then you can use for the you can use these things for different. This is they have shown for the work. They have shown one concept for the let's do this one, and top dipole and the bottom dipole. So, and both of them are orthogonal. Means wherever it has the beam, it will not have any beam. It will have null. Now this is the 3D printed high gain antenna. 3D printed high gain beam switching antenna array. So another method of beam switching or beam steering is the using the transmit array antenna. This is also very popularly used, and this will be used for the this is for the 6G also, that is transmit array antennas. So we have designed here. This is again one of the work of my student, PhD student. So here, so we have a dielectric unit cell, all dielectric, no metal is there. So that is with H is the thickness of this entire unit cell, and D is the dielectric thickness. So if phase is if one electromagnetic wave is launched here, so you will get a phase shift. You will get a phase shift with the combination of this one, that is with the, means how much phase shift it gives, that is dielectric and the air. So it is given by the beta 1 D and beta 2 H minus D, and you can calculate the if that is beta will be your K naught epsilon R D, and beta 2 will be your K naught. So this will give you the phase shift. Now, so this is our antenna setup, that is transmit antenna setup. I will discuss all this in detail later on. So your transmit antenna is there, and its holder is there, and we place different antennas at these locations. So at these locations, so I will explain what are the. So it is DRA type of antenna, that is dielectric resultant antenna. Okay. So now the first thing is that we need to characterize the material, because we don't know the material characteristics. What type of, because generally PLA is there or another, because it is still in the evolving phase. PLA and different materials are there. So we first try to quantify. We have printed the material in this one in different shapes and measure its cat. So we have different waves in different waveguide cavities. Okay, and cat, that is PLA, that is lactic acid, that is polylactic acid samples are there, and we will try to calculate its epsilon and mu r, that is dielectric constant and permittivity and permeability of this materials using the Nicholas-Ross method. Okay, now based on that, so we got the using all this calculation. So its dielectric constant comes out to be near about 2 at 28 gigahertz, and loss tangent is 0.2 basically. So and it is very lossy. So it is very lossy material. But as you know, because of the requirement of low loss material, so the material science will help us. Means they will come up with it nowadays. So new materials are being launched. So now using these materials, so we have designed a DRA, that is the same material and connected on the open rectangular waveguide. And as I told you here, so it will be advantageous if we choose the antenna structure which will have the same E and H plane beam width. So here we have chosen the E and H plane same beam width. Now based on that different so this is unit cell. Unit cell has been so how much, let's say what we want to do a different phase shift. So there we have earlier one of the work we have shown the 4 phase shift, that is 0 degree, 90 degree, 180, 270 degree. Here we have tried to get the phase shift of means more finer structure. So the more finer, you will have lesser phase error and you will have better gain. It is you are moving towards the continuous one. Discrete structure is moving towards the continuous. But at the because it will, if you increase, it will increase the design complexity and cost also. So we have to do somewhere trade-off between these two. So the magnitude remains as same. Magnitude doesn't change. Only the phase will change. Phase will, so different heights will have different phases. So here it can be seen here. So if you vary the d distance of this dielectric material, so you will have the phase shift from 0 to, that is whatever this 0 to 0 is means just air. Air will not have it. Air will have certain phase shift. So slight phase shift. So you will have the phase shift from 0 to 360. Entire phase shift can be attained here. So now, so again, this is means just a phase calculation. So based on that, we have taken the 40 cross 40 unit cells and 40 cross, and to do that, so we have applied, we have 60 quantization state, and so we got this type of pattern. Now, if I excite here, so if I feed the at the focus of this structure, so this is, we have printed this structure, and then let's say if I feed P4, so we will have the switching off in this direction, in some particular direction. This is the S parameter, and gain is 23 dB. Sorry, gain is 23 dB. Now, if I excite P1, P2, P3, if I excite P1, then I will have some another beam. Beam in the another direction. This is just a very very high gain beam is there. Transmitter antenna is there. So this is our structure. So now you can see from here. So if P1 is on, so P1, P2, P7, so you can switch your beam from one particular direction to another particular direction. So you can see, but at a generally the beam scan loss will be always there here. This is a simulator one. This is we have measured one. So you can switch your main beam from plus minus 27, plus minus 18 degree, plus minus 8, and it is one. So if you increase more number of unit cells, then you can switch your more number of the beams more. But generally what happens, we have to think of how to compensate the scan loss. Scan loss is very important. Again, people are working on the how to improve, how to overcome the scan loss. That is the 0 dB, and what is the difference here? That is maybe 4 or 5 dB. Here scan loss is 5 dB is there. This is not good also. Also, so if you see here, the gain, whatever we are getting about the we are getting about the gain of 22 dB. But gain can be enhanced because as I told you, the material was having the loss tangent of very 0.2, very lossy material was there. Now, if you increase the loss tangent, so your gain will be further degrade, and if you decrease the loss tangent, gain will be increased. So that can be seen here. Okay. So now based on that, I will compare these two technologies, that is RIS and massive MIMO technologies. So RIS, so what is the basic difference between these two? So generally in massive MIMO, we have the beam forming capabilities. So here we will have, so numerous RF chains are there. Your hardware requirement is large, means each antenna, each chain is individual, means it will be excited. Let's say if you have 16 cross 16, so it will be fed by 16 cross 16 transmitter and receiver will be, the transmitter will be there. But here you don't require anything. Here just you have to shape the beam. Just the beam will be, whatever the beam will reach here, you have to shape it properly such that it will re-radiate the signal in a particular direction. So RF chain requirement, yes, here, no. baseband processing. Here the baseband processing is required. Here no baseband processing. Cost is high. Cost is low here. Power consumption is very high and is very low. Very less power. But still few challenges are there. So people are working on it and people will try. They are trying to implement it. How the challenges of RIS can be overcome. That is okay. Now, thank you. If you have any questions, you can ask me. I will try to answer these questions.
Thank you, sir. Thank you for wonderful presentation. I would like to take the questions from the chat box and I will repeat to you, sir. What techniques can improve phase control in RIS unit cell?
Phase control.
Yes, sir.
What techniques can control the phase? Okay, phase control.
Yes, sir. In unit cell.
Let me check. Okay, so here if you see here, so the phase control. Now, if you choose the different heights of this cavity, not cavity, if that is substrate to or patch to ground structure, so this will give different phases at different frequencies. It is basically the electromagnetic wave is going here, means it is patch, then you have a ground. So it will go here and you will go back and return it. So you'll have the phase change. So different phases will be, different heights will be give you different phases. Now, yeah. So this is one way. Maybe you can place different varactor diodes can be placed, because varactor diode will again, if you have the different biasing voltage, then then different phase shift, because varactor diode is what? It is just a capacitor. Capacitor means just a phase shift. Just a phase shift. So it will give the phase shift, and it can be used for different. If you change the bias voltage, then the phase shift can be obtained. Does it answer the question?
Yes, sir. I am just moving to the next question. How does the space between the unit cell affect the beam forming?
How does the
space between the unit cells? Space between the unit cells in RIS affect the beam forming.
Okay. Generally, what happens? Generally, whenever we analyze the unit cell, so we take this unit cell, we incorporate the distance also. It is not like that just we analyze this unit cell. Maybe some distance here, maybe some x distance here, because it is infinite surface. So it will be like this. It will be means in the x plane and the y plane. Then you analyze this RIS structure in that way.
We are going to move to the next question. Can we implement adaptive techniques for RIS?
Adaptive?
Yes, sir.
Adaptive beam forming.
Maybe they are asking in terms of
adaptive beam forming. Generally, adaptive beam forming cannot be. See, adaptive beam forming is what? It is something like digital beam forming. Digital beam forming is just a, as I told you, that is in this one. I don't have any idea about it in this structure. Yeah, in this structure, the adaptive beam forming is used. Means they have used that is system view software, means just a digital beam forming they have used to generate the phase shift. So the required phase shift they have used here, it is written that is the system, they have checked it with the system view software, and that is the digital beam forming can be used. So that is RIS. In RIS it cannot be used. This is used for beam steering or beam digital beam forming. It can be used. Okay.
We are just moving to the next question. Which one is efficient in terms of power levels, MIMO or RIS?
See, MIMO, as I told you, power level, as I told, I have shown you the MIMO and this one. The massive MIMO, so the power level is very high coming because you have, let's say if you have n cross n, so you have n transceiver chains, and so each transceiver chain will have transmitter. It will be transmitting the signal. In RIS, you don't require any transmitter, just you have to switch the beams here. Just you have to switch on off the diode or maybe change the bias voltage. So by using the FPG, it will not require much power. So RIS is much more energy efficient than the MIMO structure.
Moving to the next question. How should bias lines be routed to minimize electromagnetic interference in the RIS functionality?
That you have to check by the electromagnetic solver. There is no thumb rule is there. Generally, electromagnetic solver, because you have to move the bias line from one direction to another direction, and check into the electromagnetic solver, that is installed HFSS or CST Microwave Studio. It means whether do the simulation, whether you are getting the desired pattern or not. If you're not getting the desired pattern, then you move the bias line. There is no hard and fast rule is there. See, you do these bias line this side, so there is no hard and fast rule is there.
The next question, how to choose varactor diode? Kindly explain.
Okay. That is very crucial question. That is very, how to choose. The main thing is that at what, that is there also we stuck how to choose the varactor diode here. So that was, we are not able to, main thing is that, let's say you buy the, means first see the data sheet of the varactor diode. Means at what frequency you want the characteristics. Means the generally in data sheet it says that the varactor diode is applicable till this frequency, maybe 6 gigahertz or 20 gigahertz. Higher frequency varactor diodes are costly in nature. You can use the low frequency to the high frequency, but make sure that you characterize your varactor diode using whatever the experimental method you calculate, because it will work. We tried to do that, but we are not able to complete it because the student has completed his MTech. Okay, so in the main thing is the data sheet, whether at which frequency this varactor diode works.
So moving to the next question, RIS is suitable for airborne radars?
I don't think. Airborne radar means for, can you give some more explanation on the airborne radar?
Asked in the chat box, sir. Maybe we'll move to the next question. You just repeat the question. Participant who asked the question, can you elaborate the question and ask us once again?
Yeah.
Sir, moving to the next question. What are the design strategies for achieving wide angle beam steering using RIS?
That is a tricky question. That is very wide beam width, no? Wide bandwidth or beam width?
Beam steering, sir. Wide beam steering capability.
You increase the number of elements. So you will increase the beam width. Means increase the number of elements. But as such, means you cannot increase, go beyond certain level. So it has to be some trade-off. Generally, in the literature, they have shown 16 cross 16. They have shown. See, if you see in ISRO satellites, so they have much more. Means it is not shown. They have much more beam steering in their in their satellites. That is GSAT-10. So which is high throughput satellite HTS they have. So there the beam steering is much more. Means all India is divided into 28 main beam and numerous hundreds of minor beams. Okay.
Moving to the next question. What type of materials like pin diodes, varactor diodes means are most efficient for enabling wide range beam steering in unit cell?
Again, you have to do it and check it. I don't have any knowledge on it. I cannot comment on it. Means you do the experiment. To check the varactor diode, take the data sheet of the varactor diode or the whatever the pin diode or diodes from the data sheet and try to fit these things into EM simulation and get whether you are getting the wide beam width, because general comments cannot be provided for these questions. Okay, wide band means generally the data sheet means it will give you the resistance, the reverse bias capacitance, on resistance, off resistance, all these things will be given in the data sheet.
So moving to the next question, how will be the SDR architectures for 6G?
Still in the nascent stage, still it is going on because 6G has not been finalized. What is the architecture? Because it has to be launched in 2030. 2030, long 6 years. 6 years is there. So still in the nascent stage.
Okay, sir. Participant, if you have any questions, you just type it in the chat box and we will take the questions for you. Sir, next question is, what substrates should we consider for designing the RIS?
What substrates?
Different types of substrates. Which substrates maybe we need to consider for designing the RIS?
Means you can use the people have used FR4, people have used FR4. FR4, they have used duroid material.
Participants, if you have any questions, you just type it in the chat box. Sir, one more question. How does the RIS account for mutual coupling effect between the adjacent unit cells?
How does? I don't.
How does the RIS design account for mutual coupling effect between adjacent unit cells in RIS? Mutual coupling.
Mutual coupling, again, you have to do the simulation. Means it cannot be, see, as I told you, it cannot be comment on it. So first do the simulation, get the means EM characteristics of your structure, then you can comment on it. Okay, let's say whatever we did it here. So just take the unit cell and do the coupling here. Unit cell means just a unit cell means you are not doing you are making it in infinite plane in the x direction, y direction. Okay. Okay, next.
We are just moving to the next question. What are the maximum and minimum phase shifters?
Maximum phase shift.
What is the maximum and minimum phase shift for our proposed meta atom? Maybe they need to check. Can you check the question once again, participant, and just let us know? So that's it from the chat box. We'll just wait for 2 minutes. If there are any questions, participant, please, if you have any queries to ask, you just type it in the chat box. We'll take it for you. That's it, sir. There are no more questions. We'll just, Swarnima, you can hand over the session.
Thank you, Sai. Thank you, Professor, for delivering such insightful talk today. Your talk was very valuable. I think it would have been inspired all the participants to work further in it. We appreciate your time and effort, sir. Thank you so much.
Okay, thank you. Thanks a lot.
Thank you, sir. Thank you so much, sir.